Swayam Prabha. Digital India. Educated India.
Now, my titanium trichloride molecule on the surface, this is the blue one, has one vacancy for coordination. That's the natural tendency, 6 coordinate. Other coordination you need to force them. Those are energy demanding coordinations. Okay. When you react this with AlEt3, AlEt, this titanium forms a bond with Et. Why? And ethyl group is a little bit electron rich. Not very much, little bit electron rich. Again, this man here tries to pull up electrons from here, lone pair of chloride. Okay. So this man tries to give something from here and wants to take up something from here to keep the energy balance. I will do this provided you do this for me, that concept. Okay. Now what happens is you eliminate Et2 AlCl and this ethyl inserts. Why is this? Because this is a loose bond. That's a sigma bond, no? Sigma bond electrons, you cannot donate completely, or you cannot donate. Why say completely? You cannot take away sigma electrons from a system. You can share, but you cannot take it out. But here, this is a coordinate bond. So it gives out a little of electron density, but acquires lone pair coordination, much more of electron density. I give 1 rupee and I get 100 rupees. Okay. So then what happens? This ethyl group remains as it is, the bond cleaves from here and you get Et2AlCl. These two EtAl, this forms a sigma bond with this one now. Okay. And then once this goes out, you have created a vacant site here. The chloride has gone out. Again you put one molecule of ethylene. Right? Pi electrons coordinate. Right? I showed you a mechanism some time back. Same principles operate here. Electron density, like I can write this in this manner also. CH2, no? This pi bond, this, they kind of tend to interact with each other and share electron density. Okay? So, then what happens? This ethyl joins up with this and creates a coordination here. Why is that? This is a mixture of sigma, this complex that you get is transient, is a mixture of sigma and pi bonds. And what I get now is a proper sigma complex. And I have created one vacant site. So next molecule of ethylene again sits here. Again the same thing happens. This goes and joins up here. So this keeps on repeating, cycle after cycle. So why do you need a Lewis acid? TiCl 3 is also a Lewis acid. Triethyl aluminum is also a Lewis acid. Which is the stronger Lewis acid? Uh, huh? Triethyl aluminum. Why? What you told is right, but why is that? Hmm? You see the 3D configuration of aluminum 3 plus. Does it have any electrons? Hmm? Moreover, if you see the periodic table, aluminum is a P block and titanium is an early D block. So, which size is bigger? Which size is smaller? Aluminum or? Yes. So, small charge, small size and high charge, aluminum 3 plus versus larger size and same amount of charge. Who will have more tendency to take up electrons? The one with small? Why is that? Tell. There is absolutely nothing wrong if the answer is wrong. Don't be shy, tell. What you told is correct, absolutely correct. But why is that? Hmm? You can discuss, no problem. I give you 1 minute, you can discuss. I will give you one clue, charge by size ratio. Hmm? Huh? Effective nuclear charge. Who has higher effective nuclear charge? Effective nuclear charge, aluminum has higher. If effective nuclear charge is higher, then its attraction for the electrons is also higher. Alright. So, your electrons are horn-locked with your nucleus, you do not have much chance to do anything else. Then what will happen? Any source of electron it will take. I have certain number of electrons. In both cases, you will see that there is absence of d electron in both ions. That factor is constant. Charge by size ratio. In case of aluminum, the size is small, so that ratio is higher. Okay? So, that gives rise to the tendency of effective nuclear charge. Okay? See, if the effective nuclear charge is high, then what happens? It has more control on the electrons, isn't it? The electrons are locked by the nucleus. Now, such a compound will have more tendency to fill its d orbitals and will take up any source of electrons that can fill the d orbitals. Is it clear now? So that is the reason why aluminum 3 plus is a, a Lewis acid, is a better Lewis acid as compared to titanium trichloride. So with respect to aluminum triethyl, with respect to aluminum 3 plus, titanium 3 plus is a Lewis base. With respect to each other, okay? So that is the reason why this happens. Okay? Now you will say that if I take boron and aluminum, I can do the same thing. Boron and aluminum, we can do the same thing. If I take boron trichloride and put triethyl aluminum, which is a stronger Lewis acid, triethyl boron or BCl3 or AlCl3? That's a stronger Lewis acid, right? So can it remove the aluminum this thing? The answer is no. Because in the small P block systems, higher coordinations are not possible. Higher coordinations are possible only in transition metals. Okay? Because what you have to do in the process is you need to create a coordination vacancy. Okay? And that can only happen if you have a transition metal and a Lewis acidic main group or P block metal. Okay? Instead of triethyl aluminum, you can also take triethyl boron. That will also work. Is this clear? So this is the sum and substance of Ziegler-Natta polymerization. So these two gentlemen were awarded the Nobel Prize for their discoveries in the year of 1963. Now you can see people use a variety of combination of reagents. The commercial technology is based on Ziegler-Natta discovery. These are some of them. Can have MgCl2, TiCl4, AlR3, TiCl3, AlR3 along with some Lewis base, etc., etc. Yeah, some of the commercial systems. So a lot of commercial systems are developed based on this discovery, which work more efficiently than the normal thing. Now you will ask me why all this is done. You already have Ziegler-Natta polymerization. The primary reason is what is a catalyst? Traditional definition of a catalyst. It lowers the activation barrier for the reaction. So it speeds up a reaction without getting consumed. Right? For most of the homogeneous system that doesn't work. It gets consumed. Because at the end you have to kill the system. But in case of heterogeneous you can do this. So these are all heterogeneous systems where the investment into the catalyst is not regular. Nobody wants to spend too much money. A businessman is a typical businessman. I will invest less and get more. Right? So once you do the investment, you don't have to, once you invest into your catalyst synthesis, you don't have to do it again and again. After a few cycles, you may have to do it, but not very regularly. But if you take a homogeneous system, you have to do it after every cycle. That becomes more expensive. Now, when you talk of propylene, this is how the chain can look, this is how the chain can look, this is how the chain can look. Okay? When you talk of styrene, same thing, but instead of methyl, you have phenyl. Now, depending on the relative position of the methyl groups, three different scenarios arise, at least three different scenarios. This is called isotactic, where all the methyl groups are on the same side. Right? This is called syndiotactic if they alternate. And if there is no specific pattern, then this is called as atactic. Now you will ask me that what is the use of knowing about these kind of configurations, because the physical properties associated with these three kind of polymers are very different. Okay. Usually the physical properties of the atactic polymers is the worst, only fit for making maybe plastic bags. But if you are talking of engineering plastics, which have engineering applications, high temperature applications, lot of components in space vehicles are also used using engineering plastics, then all this becomes important. So you need to make a catalytic process for making polypropylene, which either gives you this or this. If you make this, you don't get any credit. You either have to make this or this. That is the level of research what people do today. Okay. This you can only use triethyl aluminum and get this. No problem. But this and this has to be done carefully. Okay. So how much time we have? Time is still 1 o'clock, right? Up to 12:30. Till 1 o'clock, no? Okay. All going above head or it's okay? Huh? When it goes above head, you tell me, I will stop. Now, these are some of the industrial process where people have been able to make Ziegler-Natta's catalyst, where you get either syndiotactic or isotactic polymers. Okay. You have heard what is metallocene? Huh? So, normally Ziegler-Natta polymerizations do not have much of scope for making syndiotactic or isotactic polymers of very high molecular weight. Moderate molecular weight you can make, but then if you have to make for very high molecular weight, those plastics are very expensive and you need to use metallocenes. I hope you know what are metallocenes. The easiest example is ferrocene. Ferrocene, the brother of kerosene. Okay. Okay. So let us see some of the compounds where some of the catalysts for this using metallocene. Now, why homogeneous catalysis becomes important? These are the reasons. The mechanisms of reactions can be understood only if you are able to study them. One of the easiest techniques to study them is to use spectroscopic techniques. So, when you use spectroscopic techniques, then it's preferable to have a soluble system, homogeneous soluble system. That is number one. Now, usually it is seen that the catalyst amount that you need for making a polymer of a certain physical properties, if you use the homogeneous method, the amount of catalyst loading is much less. Okay? If you use a heterogeneous system, the loading is higher. There is one common problem with heterogeneous system is poisoning. Okay? That problem is also not there to that extent for homogeneous systems. And second is that if I have to make a polymer of a certain molecular weight, other side reactions, the extent of other lower molecular weight or even further higher molecular weight, those fractions are less if you use a homogeneous system. Okay? Mostly the metallocene polymerizations are homogeneous. They are expensive polymerizations, so the cost of this exceptionally high molecular weight engineering plastics is high. Now let us see how these are made. If I have to make a complex like this, Cp2, zirconium, CH2PH, THF, THF is coordinated THF, BPH4. I use Cp2 zirconium dibenzyl, CH2PH2 plus this complex here, Cp2Fe, BPH4, and I get my catalyst here. Cp2Fe comes out as a side product, and this is also another side product. This and this can be easily separated, and you get your mixture. Now you see the same thing can be done using AgBPH4. Now the difference is that this CH2PH is eta 1 and this CH2PH is eta 2. You know what is eta 1, eta 2? Huh? Hapticity. Another one, if I take Cp2 zirconium dimethyl and react it with this borate salt, I can get Cp2 zirconium plus followed by this group here and where this boron has a negative charge. So overall the molecule is neutral, but the zirconium system has a plus charge and the boron has a minus charge. Are you able to follow all this? Huh? Sure. Now what about alkynes? You can polymerize alkenes. What happens with alkynes? Can you polymerize alkynes? You can partially do it producing oligomers. Here is the catalytic cycle for alk-1-ine oligomerization. That means terminal alkynes. Internal alkenes or alkynes don't polymerize. We talk of only terminal systems. What happened? Water. Water sharing. Water sharing is a problem between people, between states, right? Everybody fights for water. So CP2, CP start to zirconium, 1 methyl and 1 borate. This reacts with the alkyne. This is a terminal alkyne. And you get this complex here where where this is inserted, you see, same like alkenes. Now this can react with the second molecule. It can eliminate this fragment CH2 and you can get this one and then the cycle moves on. Now this can react with another molecule of the alkyne. Now you see how the chain grows. Now the chain has gone on after the insertion. Now the third molecule comes in, again it inserts. So you get alkene, alkene, alkynes. So finally you can get this. Alkyne insertion. So alkyne is getting reduced to alkenes. Okay. How do you make this CP2 titanium dichloride? CP is eta 5 CP. This will probably be a little easier to understand. You can take the monomer. Normally, two molecules of this dimerizes, Diels-Alder reaction. So you take the dimerized part, that is how it is commercially sold, CP dimer, and you need to crack it at very high temperature. And you get this compound, which in a few hours of time again dimerizes back. So this can react with N-butyl lithium. You can get the lithium salt. So one of the hydrogens get removed. So you get the negative charge. So this becomes aromatic. Now this reacts, two molecules of this reacts with titanium tetrachloride. You can get the dichloride and then you do a Grignard synthesis. You can get the dimethyl. Okay. Same thing is true with zirconium. Now this is also a olefin polymerization catalyst. Instead of Cp, you are using Cp star. So Cp star H is like your Cph. This reacts with N-butyl lithium, you can get CpLi. But here, if you react this with titanium tetrachloride directly, titanium gets reduced to titanium 4, gets reduced to titanium 3. So people don't use that. You can react it with Me3SiCl, so you get Cp star SiMe3. Then you react it with titanium tetrachloride, so you can get this. Your compound with the elimination of Me3SiCl, and finally you can react this with a Grignard reagent. Okay. What about this? You take this and react it with, reduce it with LiLH4 in the presence of minus quinine. You do an asymmetric synthesis. You get this compound here. So this is an chiral center. So you are making a chiral catalyst this time. Here you have your Cp hydrogens, one hydrogen here, one hydrogen here. If you react it with N-butyl lithium or methyl lithium, you can generate the anion, and this can react with C5H5 zirconium trichloride. Okay. So you will liberate lithium chloride because your counter cation is lithium here, and then you can make RCpCpZr dichloride, where both the Cp groups, this Cp groups and this Cp group is different. One is a chiral Cp group and the other one is a achiral Cp group, normal Cp group. Chirality has a profound influence in the tacticity of polypropylene that you get. Okay. Done? This is another type. Let's not get into the details of this. This is more difficult. So these are all quite difficult systems. Now let us see the ones which are of commercial importance. So these are all the catalysts of commercial importance. Some of the examples you don't have to write. This is not easy to make. 1 gram costs more than gold. 1 gram of gold is 10,000 rupees. Here each of them 1 gram is more than 25,000 rupees. So this is more expensive than gold. Huh? You want to make? Start your own business? No problem. Come, I will teach you. It takes 6 weeks to make 1 gram. Okay. So the biggest producers of this one, polyolefins. Who is the biggest producer of polyolefins in India? Huh? Hmm? Who Who is the richest man in India? Ambani. Reliance Petrochemicals. Who is more rich, Ambani or Adani? Ambani is more rich, eh? Okay. Now the problem with the metallocene systems that we have discussed is that these ligands are very expensive. I told you, no businessman wants to invest money into business. They want to invest little money and get maximum output. Okay. So those metallocenes, what we have seen is used for making very high quality, high strength material, plastics basically. Now what about moderate strength material? Atactic material, Ziegler-Natta catalysis. Simple Ziegler-Natta, no problem. What about moderate strength? Neither this side or that side. So for them you use non-metallocene kind of ligands. Okay. So here is one example. This is 1,2-diaminocyclohexane. If you react this with 2 equivalents of butyl lithium, you can generate a lithium salt here and a lithium salt here, NLI, NHLI and so NHLI. Then react it with Me3SiCl. LiCl will eliminate and you will get this compound. Then you react it with 2 equivalents of N-butyl lithium. So you can generate N minus here, N minus here, NLI, NLI, right? Then that you react with TiCl4, you can make the titanium dichloride with the elimination of lithium chloride, and then you do the Grignard. Huh? Who? Yeah, regularly. All of you are in class 12 now? Which class are you in now? Huh? Oh, just finished. Okay. How many of you are going for medicine? Huh? Oh, second year MSc. Okay. So how many of you are going for a PhD? Wow, all of you, almost. Where? Where you are going? Okay, you have to clear those exams. Okay, who has cleared GATE? This time you will again write? CSIR, JRF? Okay. Prepare well. Any problem? Come to me. Okay. So here is another example. This is called as the Macon-Wills ligand. This is also a very famous non-metallocene ligand. So you take this 2,4,6-trimethyl-aniline, react with butyl lithium, you can get the NHLI, then react it 2 molecules of RIX, react it with 1,3-dibromopropane. In the presence of TMEDA, you can get this material. This again you can make the dianion and react it with TiCl4, you can make the dichloride and finally the dimethyl.
SwayamPrabha. Digital India. Educated India.